Transformers with integrated inductor part used for resonant converters are quite frequent type of components being modeled with 3D FEM software. Typically, such designs consist of a planar transformer made of interleaved windings and inductor made of litz wire. And let me show you how easily and efficiently we can create such component from scratch, including all the geometries, and solve this within a few minutes. As usually, we start with a general setup. This is going to be a symmetric computation. Under the electromagnetics we choose harmonic because this component runs with a sinusoidal voltage excitation at a one given frequency. For a heat transfer we will use steady state because the component itself is relatively small and the temperature changes in time, they are not significant for such type of components. Next we will move to the material section. Here, as usual, you can choose core and conductor materials, copy them from global materials to local materials. In this case we are going to use ferrox cube core material, ferrite with a defined electrical conductivity and constant permeability. When we define constant permeability, you need to be very careful not to exceed the saturation of this core material, because the software will not know that the saturation happens. It will just calculate magnetic flux assuming the constant permeability. Additionally, this core material has core losses for a wide range of frequencies that are fitted to the Steinmetz coefficients. They are thermal coefficients used for the thermal simulation as well. For conductors we have copper. Copper is going to be used for both litz wire as well as solid conductors for planar windings. Aluminium is going to be used for the heatsink that is placed on top of the component that holds it structurally together. Epoxy and fiberglass are used epoxy is used as a potting material, while fiberglass is going to be used to separate inductor part from the transformer part. Next we move to the core section. Here you can see that the core consists of two geometry groups. Both we add by clicking new group and then changing the setting. The upper part is a transformer. Geometry type for this core is PQ. We just choose PQ from the wide list of different parametric geometries in TRAFOLO. You can see all the parameters defined for this geometry. Just put numbers, click mirror to create a second piece which is mirrored on top of the primary. Also pay attention that here we use a virtual gap of 20 microns. This is the gap which here is added as a face, and on this face the software will add permeability gap with thickness 20 microns. We are not going to model this as a physical gap because 20 microns is such a small gap that if we would want to add it as a physical gap, that would create a very thin mesh element, and that's not going to improve accuracy of the simulation, while just add additional challenges for meshing and solving. Moving back to the second component, core for our component. This one as well is PQ core, just with a different height. We are not mirroring it because this is one single piece, and also pay attention that we need to translate it to move it on top of the transformer core. It's of course not going to happen automatically, so you will need to adjust yourself the translation as well if any rotation is needed. Pay attention that we are not going to apply here any gaps, even though there is going to be a gap between the inductor core and transformer core. We are going to create this gap with a separate geometry, with a separate separator. Next we move to the other tab section. Here we define the heatsink or clamp that holds the component together. There is a special type, heatsink type, where you can build parametrically based on those few parameters. Also pay attention that you will need to adjust and translate the position of this heatsink to match the position of the core pieces. Next we move to the bobbin. The first one corresponds to the potting, which could be like for thermal reasons to remove heat from air pockets between windings. But also in principle this could be not a potting material, but this could be also air domain, where you could provide effective heat conduction properties to mimic basically to mimic the thermal conduction between let's say winding turns. So the geometry is very simple, cylindrical. Let's move to the next one. This one is box geometry used for the separator between the inductor core and the transformer core. Here we also had to translate the geometry. Then we put everything together. This is geometry before assembly. I click assembly geometry. After assembly, the component is split in half and the air domain enclosing the component. Next we can move to the LMAX section, and here we will define the excitation for primary winding. It's going to be driven with a voltage. We will enable the secondary winding for the transformer, and on the secondary side we are not going to apply neither current nor voltage, but we are going to use circuits to define the impedance on the secondary side. Impedance could consist of resistors, capacitances or inductors. To separate this inductor from the primary and secondary side, we create a special type of winding which we call additional coil. This just allows us to separate this additional coil or inductor from the other two primary and secondary windings. Still, we tell, after adding this additional coil, we tell to which side this additional coil will correspond. This will allow us to define circuits in the next step. Here underneath we need to, for each of those winding groups, we need to define whether it's primary, secondary or additional coil. And after setting those winding types, you can see that we have this color scheme that tells what winding type it is. Additional coil and primary and secondary are interleaved. Also, you can switch to the terminals. Those are default terminal selections. Everything is fine here. Next, we move to the circuits. Under the circuits, you can see that the additional coil was connected to the primary winding. This connection happens through those so-called circuit netlists. Equal IDs correspond to the connection. For example, this positive and this positive node for additional coil element and primary winding element, those will be connected. The same as this primary source with ID 10 is going to be connected to the additional coil, as you can see, for example, here. So this node would correspond to the ID 10 in our case. Here, the connection between additional coil and transformer would correspond to 5. You can freely change those IDs to any number as long as they are unique and elements that need to be connected are using the same ID. On the secondary side, we have resistor added with 10 ohms to the secondary side and then connected to the ground. Do not worry that both primary and secondary are connected to the same ground. Even though in your real component you may have some isolation between primary and secondary, this ground is numerical, it's absolute, and we need to have some point of reference for the numerical solution to converge. So this is fine that we have the common ground. Next we move to the waveform section and define the frequency at which will operate our component and the RMS voltage on the primary side. Next we go to the heat setup. Here we are going to define the boundary conditions on the component, how heat is going to be removed from our component. First we are going to apply the steady state temperature. This is our best guess. We assume that it's 50 degrees. After our first simulation we can change this number accordingly. Next we are going to define boundary conditions on all faces. We assume that the temperature around surrounding this component is relatively hot, it's 50 degrees, while the heat transfer coefficient of surrounding air is, let's put like 10 watts per meter per Kelvin, which corresponds to slightly intense convection around the component. Also, considering that we have a heat sink, we can assume that there is some cold plate that is removing the heat from the component. So I am holding Shift and clicking on all three faces on the bottom of this component. You can see that they are all selected here in this boundary condition selector, and then I choose to be it as a fixed temperature. I assume that this cold plate is so efficient that it can keep those 50 degrees constant on the surface of the component. So now you can see that there are three bold faces corresponding to faces with a fixed temperature because they are different from other conditions set up for all other faces. Next we move to the meshing section. In this step we need to ask the software to evaluate the mesh parameters. You may need to click evaluate mesh the first time. In this case the software did it automatically. From our experience we know that in such cases the mesh size for windings should be about the half, at least a half of this width of the winding. This is a bare minimum just to get the first simulation running. So I assume now that this width is about 1 millimeter, so we will apply let's put like 0.5 millimeters mesh refinement on those windings. After you get the first simulation results, we can observe where those losses are mostly coming from, and then apply additional mesh refinement in those areas where it's actually needed. There is no need to run the first simulation with very fine mesh. Meshing was done in less than a minute. We get such relatively coarse mesh, but this is going to be sufficient for our first simulation run. Let's move on now to the solve section. Software tells us that recommends us to use 6 cores. I will use slightly more, 8 cores. Let's click simulation setup. It's going to prepare the simulation, calculate homogenization parameters for litz wire, and then run the simulation. While the simulation is running, you can open the terminal here on the left bottom corner just to observe the residuals and solution converging. Once the simulation is over, we get this beautiful picture with the temperature distribution. But first let's move on to the summary section, where we can find the loss distribution among the primary winding, secondary winding, and thanks to adding this inductor as an additional coil, we can see that this inductor losses are treated here separately as additional coil 1, and we can see what the loss for that winding is. These are total winding losses. The core consists of about less than half of the winding loss, and this is a surprise. Other loss corresponds to the heatsink, and we can see that there is 1 watt of loss generated in the heatsink, and this is a substantial amount of heat. As we will see, there is a reason why there is such a large heat in this case generated. Also, we can find the DC resistance of windings, and with the AC resistance you need to be very careful, because this is AC resistance not for windings but for the source, and this is resistance which would be measured from the primary winding side, and this is nothing else than just a resistor value on the secondary side. This would be the resistance if we would take a measurement on the secondary side. Next, let's move on to the magnetic flux section. We can see that substantial part of the magnetic flux goes through the inductor part of the component. There's also 0.55 Teslas of magnetic flux, which means that those areas would saturate. However, what we are mostly interested is the magnetic flux values in the bulk, which is between 0.2 and 0.3, meaning that our core in general is not going to saturate, so the usage of constant permeability in this case is acceptable. If we would get closer to the saturation, then of course we would need to definitely use a BH curve in this case. Next, we switch to the coil losses. First of all, we see that the most coil losses are concentrated for the planar winding, especially between primary and secondary, where the interleaving happens. This is due to proximity effect. It has nothing to do with a gap. There's no gap, like a big gap between primary and secondary windings. This is thanks to the proximity effect between primary and secondary currents. This also indicates for us that if we want to increase accuracy of the solution, those red areas are areas where we would need to apply additional mesh refinement. Maybe on some surfaces we don't need to mesh everything, but those areas with the red are those that we need to pay the most attention. From the litz wire point of view on the top, which consists of the inductor, we can see that this one turn on the button of the inductor part gets the most resistance and heating. That's thanks to the fringe flux. There's a gap between the core pieces, so this is where we expect the highest magnetic flux values and also proximity effect in litz wire. Next, we move to the other losses, and this is what is very interesting about this case, because our inductor core piece has all three gaps same thickness. There's a substantial part of the fringe flux that generates eddy losses, or you could call it stray losses, in the heatsink. And because heatsink is made of thick, well-conductive metal, those currents are easily induced here and generating losses. So if we would want to reduce those stray losses in the heatsink, we would definitely need to reduce the thickness of those gaps, or even remove the gaps on those outer limbs and try to create some distributed gap for this central limb of the core. Next, we move to the core loss section. We can see that most core losses are concentrated in areas where we saturate the core. And finally, the temperature distribution. This is very beautiful illustration how the temperature is going to be distributed because of very efficient cold plate on the button and fixed temperature. This was our assumption. We can see that the highest temperature is going to be for the transformer part, but not on the button, but on those upper interleaved areas between primary and secondary. This is the area where you would need to pay the most attention, because in this case we assumed quite efficient cooling thanks to the cold plate. But in case if you cannot remove the heat from the button, your component would definitely overheat, and this area of overheating would most likely be around those areas where primary and secondary interleave. We also see that there is some heating from the litz wire on the inductor part, but not as significant. both the heatsink and thermal convection, natural convection, removes the heat from the top of the component.